Hi, students. Today I want to do section 8.3, which is graphing piecewise functions and shifting functions. First, we're going to start with shifting some basic functions that we see a lot. I have three examples for us right here. These are the most basic forms of these three types of functions. The first function, f of x equals x squared, is a quadratic function, so it's going to look like a parabola. The second function, f of x equals absolute value of x, is an absolute value of function. So it's going to look like a V shape. And the third function, f of x equals the square root of x, is a radical function. So it kind of looks like half of a parabola on its side. I want to go through each of these basic forms and then show you how they each can shift. So for the first function, f of x equals x squared, I picked a few x values for us to plug in so that we can plot these points. I picked -1, 0, 1, and 2. What is really important in this function, since we know it is going to look like a parabola, is to make sure that we are plotting the vertex of that parabola, which is where it turns. So the smallest value a function of x squared can take on is going to be when x is 0, because an x squared can't take on a value that is any smaller than 0, because that squared forces any number you plug in there to become positive. So we had to make sure to have that 0 for x in our table. And then I just picked a couple points around it. So if we plug in these 4 values for x, we end up getting these 4 corresponding values for the output. When we plot those 4 points, it looks like this, and indeed we did include the vertex of our parabola. We can connect the dots, and it looks like a parabola with a center vertex at 0, 0. Okay. For our absolute value function, I use similar reasoning, picking the x values that I want to plug in. I know that the smallest an absolute value can be is also 0, so I included that point here and some points around it. When we plug those values into our function, we get very similar values as our parabola, except notice that they're not being squared. We are just taking the absolute value of them. So when I plot those points, they look like this. And then when we connect them, we get the absolute value function. For our radical function, if I use those same x values, I actually am not allowed to plug in x is -1 because we cannot take the square root of a -1. So when looking at radical functions, it's important to pick an x value that is going to make the piece of the function inside the radical equal to 0, and that value is 0. So we can really start at x is 0, and then I did 1 because we can take the square root of 1, and then the next point I picked, notice I skipped over x being 2, and I picked the next value that is going to allow us to take a square root of it, so it will be easy to calculate the output. So when we plot these 4 values, it looks like this, and we can connect that dot to get our radical function. Okay. So notice the important parts of each of these 3 functions. The vertex of your parabola, where the stuff inside the squared is 0. The vertex of our absolute value function, where the stuff inside the absolute value is 0. And the stuff in the starting point of our radical function, which is where the stuff inside the radical is equal to 0. Okay, so those are all points. You want to figure out the x value that is going to include those pieces of the function, even if other stuff around them changes. So let's start with our x squared function, our quadratic function. And I have three variations of that quadratic function that I want to go over so you can see how they shift and how we pick the x values that we want to plug in to plot points for graphing. So our first function, f of x, is x squared plus 1. When we go to figure out what x values to use here, we want to make sure that we are including whatever makes the squared portion equal to 0, because that's going to make this as small as it can be, and that's going to be the bottom or the vertex of our parabola. So the thing that makes this x squared 0 is just 0, and then I like to pick points on either side of that. So -1, 0, and 1. When we plug those in, we get, for the output of our entire function, 2, 1, 2. So we know that 1 really is that lowest point. And if we graph that, you can see that that point, x is 0, y is 1, is the lowest point on our graph. So we did a good job including the point x is 0, right? When we come to our second function, f of x is x plus 2 squared. Notice that we are adding 2 to the x before we are squaring it. So if we want to figure out what value of x is going to make this squared piece equal to 0, we need to figure out what value of x makes the stuff inside parentheses here equal to 0. Well, that's going to be when x is a -2. So that tells us our vertex is going to be when x is at -2. So we want to make sure that we include x as -2 in our table. And then we want to pick points on either side of it. So here I picked -3, -2, and -1. When I plug those values in, you can see that when x is -2, that is the lowest point on our parabola. And we can graph it, and it looks like this with the vertex at x is -2, y is 0. Now we come to our most complicated quadratic that we have here. And you see that we have a negative out front. So what that's going to do is kind of flip everything here before we add the 3. But we're going to pick our x values the same exact way. What is going to make this squared piece as small as possible? Well, that's when x is a +1. When x is a +1, we have 1 minus 1, and this thing inside the squared is going to be 0. And that's as small as you can make something that's being squared. So x being +1 is going to be where our vertex is. So we want to pick x is +1 and then points on either side of that. When we plug all these points in, we get these values, and it'll plot like this. So when x is +1 happens to be the vertex parabola, and because we have this negative sign out front, everything actually gets flipped upside down. Okay. So that's quadratic graphs and how they shift. Take a look at these to notice that when we add a 1 outside of the squared, it shifts us up by 1. When we add a 3 outside of the squared, it shifts us up by 3. But when we add inside of the squared, it shifts us left. And when we subtract inside of the squared, it shifts us right. Oops. Let's take a look at some absolute value graphs. So I've got 3 absolute value graphs, and they behave very, very similarly to the quadratic functions. The only difference is that shape is more of a V than a U. So we go through pretty much the same process. We want to here make sure that we're choosing an x value that is going to make the absolute value portion equal to 0. And then we want to choose points on either side of that. So our first function, the absolute value of x plus 1, we want to make sure we include x is 0 and points on either side of that. When we plug those in, indeed, that is going to be the vertex of this absolute value part. And when x is 0, y is 1, this plus 1 has shifted us up 1. For our second function, absolute value of x plus 2, notice that the plus 2 is inside of our absolute value bars, so we now need to take that into account. The smallest value this absolute value can take on is going to be 0, and that's going to happen when x is a negative 2. So we want negative 2 to be included in the points that we plot, and we want to choose points on either side of negative 2. When we plug in those values, we again have reached the bottom of our parabola. And you know what? I just realized we've got some errors right here. Just want to jump back real quick. My f of x values were incorrect in that last example. When we plug in the -1, 0, and 1, we get a 2, 1, 2 out. Because we've added that plus 1, it has shifted us up by 1. Now to our second example, we need a x as -2 is going to be the smallest this absolute value can be. So x being -2 is the x value we're going to choose for the middle and choose some points on either side. And then we're going to calculate the outputs of our function. And you see that adding a plus 2 inside the absolute value bar causes us to compensate by making the lowest point at x is -2. So it essentially shifted what we call our parent function over to the left by 2. Now let's take a look at f of x equals absolute value of x minus 1 minus 3. To think about the x's we want to plug in, we just need to look at the absolute value portion. The smallest this can be is 0, and that's going to happen when x is positive 1. So we're going to pick x as positive 1 and then some points on either side of that right here. So we got 0, 1, and 2. And then for our outputs, we'll plug them into our function there, and we get those as our outputs, which makes our function look like this. So notice that this -3 has shifted everything down by 3 points. So our lowest point when x is 1 is at -3 because of this -3 on the outside of our absolute value. But the -1 on the inside of our absolute value has shifted us to the right one in the positive direction by 1, because we had to pick a x as a positive 1 to compensate for that -1. Okay. Now let's take a look at a few radical graphs. Radical graphs are a little bit different in that we need to really think about the smallest value that we can plug into our radicals, because you cannot have negative numbers inside of a square root. So in our first example, f of x equals square root of x plus 1. The smallest value that can go under this radical is going to be a 0. So the smallest value x can take on is 0. So we're definitely going to want to include a 0 for x. And then we're going to want to pick some numbers larger than 0 that we know we can take the square root of. So we picked a 0 because that's the smallest number that can go into our square root. So that's going to be the beginning of our domain. It's going to be 0 to infinity. I picked a 1 because we can take the square root of 1. And then I jumped all the way to 4 because I can take the square root of 4. So we'll plug those values in and we get 0 plus 1 is 1. Square root of 1 is 1 plus 1 is 2. And square root of 2 is 2 plus 1 is 3. So we can plot those points and notice that this plus 1, just like in all the other types of problems, when you add something to the outside, it shifts in the y direction according to that addition. So if we added a 1, it shifts us up 1. In our second example, f of x equals the square root of x minus 2. Now our -2 is included inside the square root. So we're going to do the subtraction before we evaluate the square root. We need to consider two things here. One is, what's the smallest value of x that we can plug in here? Because we're going to subtract 2 from it before we take the square root, the smallest value of x we can plug in is going to be a positive 2. So our domain is positive 2 to infinity. So our smallest x value is going to be positive 2. Then when we start to think about some other x values we want to plug in, we want to make sure that after we subtract 2 from them, we can take their square root. So I picked 2 and then a 3 because 3 minus 2 is 1. We can take the square root of 1. And then a 6 because 6 minus 2 is 4. I can take the square root of 4. Okay, so that's our outputs, and our graph is going to look like this. This negative 2 has shifted us to the right by 2. So the smallest x value is x's positive 2. Now in our final radical example, we've got a couple things going on here. We've got, we're adding 2 before we take the square root. We're subtracting 1 after we take the square root, and we also have a negative sign in front. That negative sign in front is going to flip our graph upside down. This positive 2 is going to shift us to the left by 2, and this negative 1 is going to shift us down by 1. If you want to plot some points, make sure pick an x value that is going to make the thing inside the square root 0. So we want to pick x is negative 2 for our smallest x value. So our domain is negative 2 to infinity. And then I just picked a couple x values that I know I can take the square root of. We find their corresponding y values and we graph it. So the starting point is at x is negative 2, y is negative 1, and our graph is flipped upside down because of that negative in front. Finally, let's take a look at piecewise functions. Each part of the function is restricted to a piece of domain. That's how piecewise functions work. Each part of our function is restricted to just a portion of the domain. That means only certain x values are plugged in for one part of the function, and only certain x values are plugged in for another part of the function. When you do a vertical line test or just run a vertical line across your graph should not overlap each other. The important thing is to notice how the function behaves right at the transition. So our example, f of x is 2x plus 3 for all x values less than or equal to 0, and it's negative x minus 1 for all x values greater than 0, but not including 0. So when you take a look at the graph, notice that our function behaves like 2x plus 3 for all the x values that are smaller than 0. When x is actually at 0, it also behaves at like 2x plus 3 because we are including the point x equals 0 in this first piece of our function. Now, for all x values greater than 0, our function behaves like negative x minus 1. Notice we put this open circle here to indicate that when x is 0, we are not down here at negative 1. In fact, when x is 0, we are up here at 3. Right? And that's piecewise functions. Get started on your homework and good luck with everything.